Okay, so let's invite our next speaker, Professor Ranjit Challa from UCSD. So it's my pleasure to introduce Ranjit for this next keynote. So Ranjit is a professor of computer science in University of California, San Diego, and his interest is programming language and software engineering, specifically for building reliable computer systems. So I have grown up studying Ranjit's paper, specifically BLAST, from in Microsoft days. So yeah, looking forward to Ranjit's talk. Thank you.
Okay, well. Here we are. Thanks. Okay, so I'm going to be telling you about some work I've been. This is actually Nico's work. Nico is my PhD student. He's fantastic. He's going to give a talk at PLDI. This is kind of the director's cut version of it because it's a bit longer and it focuses a bit on the analysis aspects which Nico will not be able to talk about. Okay, so let me begin by just a bit of a troll. This damn thing doesn't work. Sorry. I have a problem with program analysis, okay? And my problem with program analysis, roughly speaking, is this. Is that in the program analysis world, we always set up this dichotomy between the people who write the programs and people like us who write the analysis, okay? And there's this kind of wall between the two of us, and we assume the programmer is sort of, is this person who's doing, as Devin just said, offset tricks, and we have why do you do these things? Why do you make our lives so hard, right? And so the programmer can't really affect. We have this notion that the program is written. They can't really affect what is being verified, and the analyzer again is this. We're worried about false positives and false negatives and so on and so forth, but we can't really influence how the program was written in the first place. And so what I've been working on for the past sort of N years, 10, 15, I don't know, is a way where these two people can be the same, okay, where I want to do the verification sort of during development, not afterwards, in the more kind of in the program verification style, if you wish, but trying to use program analysis to alleviate a lot of the work that you normally have to do with program verification. Okay, so what do I mean? Well, first of all, I want the analysis to be able to affect how the program was written. So for example, as you'll see, we worry a lot in program analysis about, well, did you get a false alarm? Or is your analysis very precise? Do you have a real bug? And I argue that there's a missing dimension here, which is how quickly did you report the error? And something that was a false alarm, at one point in time, if you sort of reported it early enough, then they would just fix the program. It would not really be such a big deal. But if you report it 6 months later, then it's like, I don't care about this. I can't fix this error right now. I don't want to deal with this. And this has been something that academics like me sort of have speculated about for a long time. But there have been several nice studies from large tech companies where they built static analyses and they've sort of measured, how people sort of react to them that really validate this particular hypothesis. Perhaps closer to my heart, what I care about is I want the program to affect what properties to check and how to check those properties as well. Okay, so I don't want this necessarily to only be in the hands of the sort of analysis designer egghead. I really want the programmer to be able to control this in a somewhat easy way. I don't want to make it terribly onerous as well. And in particular, I want the analysis to sort of scale up nicely. If you do nothing, you'll just get some baseline, maybe you care about null dereferences, or maybe you care about array bounds, or maybe you care about integer overflows. These are just sort of baseline properties that everybody cares about. But then as you if you pay more, then you will get to check more things about your program. So this is what I mean by this kind of program can influence the analysis as well. And so the way we've been trying to do this for the last sort of N years, whoa, that was too fast, is by building something called a refinement type system. So you can think of it as a kind of type system on steroids, and I'm going to kind of describe this in a moment. And in the first part of this talk, so I've been doing this for like 15 years, and for the bulk of these 15 years, the work has all focused on, if it's a type system, you're probably doing it for a functional language. And yes, we did do it for a functional language. So it was like Haskell and OCaml. And people are always like, well, this is great, it's a functional language. What about real programs? And, I love functional languages. Like, well, one has to have a tough skin. And I think the really nice thing about Rust is, I think we finally kind of cracked this problem of making nice types, refinement types work in the imperative setting, and I hope to sort of persuade you about that. Okay, so I'll show you how Rust's Rust design sort of really makes it quite nice to write specifications in this refinement style, which I will explain. I don't expect you to know what refinements are at all. And then the second part of the talk, depending how the time situation works out, I'll tell you how the analysis sort of works under the cover. So if you wish, this is like the demo, and this is we sort of peel back the covers, and I'll show you how things work sort of under the hood. And then I'll sort of briefly describe some results that we have using our tool that we've built over the last couple of years. Okay? And also just interrupt me. The next bit is supposed to be a very interactive demo, so I hope you'll interrupt me. Maybe Peter can heckle me with some tricky questions, I hope at least. Okay, so part one, refinements and Rust. So I'll tell you what a refinement is, and I'll give you a brief Rust tutorial. If you don't know what Rust is, well, it'll be fine, don't worry. I don't much know what Rust is either. It's a very complicated language. Okay, so we've been building this system called Flux. And the key idea in Flux is that you can make refinements, which are a very kind of, if you think about type systems, they work very nicely in a pure setting. In Rust, the whole sort of, the key sort of notion in Rust is this idea of ownership. And what I hope to persuade you is that once you have ownership, refinements can kind of come along quite nicely and in a very ergonomic fashion. Okay? So, specifically, I'm going to sort of explain this in 4 little steps. So first, what I'm going to show you is what we're going to do is we're going to take plain old types like int, bool, that kind of thing, and we index them with values. And I'll explain what this means in a second. Next, I'll show you how you get the first kind of updates. What the hell? Not that kind of update. What happened here? Loose connection, rats. Ah! That's no good. Let me unplug and replug. Talk about update. What's his name go? Okay, there we go. Okay, I will have to be very gentle and not, can I not touch my computer? Okay. Then I'll tell you how we do sort of updates. And then we'll get to the more interesting bits about the language, which is how do things work with shared and mutable references. Okay, so let's begin just with refinement type, sort of 101. What is a refinement type? Okay, so in the Rust setting, so you need not have known anything about refinement types before. What we're going to do is we're going to start with base types. I use B in green, and I'm going to index them with think of it just as a pure value. So concrete example, I32 5 means the singleton type I32 that is literally equal to 5. Okay, so I32 is like all 32-bit integers. I32 5 is literally the integer 5. Now, why would you want a type for that? We'll get to that in a second. Okay, let's look at a couple of more examples. Booleans are true and false, except if I now index it with true, then what that means is it's the singleton Boolean that is literally equal to true. Okay, so let's look at a quick demo if I can not have everything blow up. Okay, so here is, here's a function, I call it TT, it returns bool, and let's see how good Copilot is, shall we? So here what I'm going to do is, there we go. Okay, so Flux, so this is, it's kind of, except that we don't for some reason like the name over there. So this is bool true. So what I'm saying is I'm a function, I return not just any old bool, I actually literally return the bool true. So if, for example, I change this to false, then the type checker will yell at you. Say, well, I don't think so. Okay, this is definitely not false. Okay, so let's not call it false. Here, instead of relying on Copilot, let's do the old-fashioned copy-paste. Okay, so you can see this. Here I'm going to say bool false. Okay, so far so good? Now here's the fun thing you can do with bool. You can write a function that encodes assertions. Okay, so here's a function whose precondition expects only true. Okay, so let me pull this up a little bit for you so you can see this nicely. Are the fonts large enough at the back? You can see this, yeah? So what this says is, I'm a function called assert. I take as input a boolean, I don't do anything of any consequence, but the only argument you can pass me is true. Okay, if you pass me anything other than true, then shame on you. So for example, I can now call assert 1 less than 2, which is of course true. But if I make this 10 less than 2, then the type is I don't like that, because 10 less than 2, not true. Okay? And now what's happening under the covers, I will explain what happens under the covers in the second half, is that there's a little SMT solver, there's a little sort of program analysis that's running, and it's sort of checking, does 10 less than 2 evaluate to the Boolean true or not, okay? And as you might imagine, the same thing works with integers. So for example, here's a function, I call it 5. It takes as input, it doesn't take any input, it returns a U size 6. This is of course correct, but if I change 6 to 60, then it will yell. Okay, sorry, it cannot be proved naturally, and it sort of underlines it's not equal to 6. If instead of 6, I change this to, fine, 2 plus 4 is as good as any other thing, then it'll be quite happy. This red thing is bothering me, so if you don't mind, I'm just going to fix it, and I'll make it 20. Okay, so far so good?
Are the bounds for use size checked?
Ha 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 ha. Very good. We'll get to that in a second. The short answer is yes, they are, but, well, yes. Okay. So let's look at a slightly more interesting, who cares about bools, true and false. So in this sort of, as we do this demo, I'll also sort of weave in a small array bounds checking, like how do you do array bounds checking in this style. Here's what we're going to do. I'm going to rig it, so for example, if I have, the vec is the kind of, I don't want to say bread and butter, it's really the workhorse kind of data structure in Rust. And here what I'm going to do is I'm going to take vecs, and I refine them with an index. So this is, I can show you the definition. There's no secret here. So for example, here is blah, 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 blah. Here we go. Here's vec. It's literally a wrapper around vec. It does nothing complicated. It just has a field called inner, and which is a vec. Except that I'm now sticking this index, which is going to track the size of that vec. Okay, so just like with bools, we took true or false. With int, we have the actual value. With vec, maybe I care about how long they are. And so I'm going to refine them with this index. And so here, look at the API for vec. It says that it returns a vector whose size is 0. So notice we're not checking anything about vector because this is being implemented by the Rust vector library. Yeah?
Is int online pointing, is that a bit of Flux syntax?
Oh, very good, very good. This always happens. Excellent. I didn't think we were going to go there. So, very good question. Let's pop back to my slides. Let me flee to my slides to answer this question. What's going on with these pure values, this purple stuff, is that these are all things that an SMT solver can understand. So these are pure. This is like in the realm of logic, if you wish. And so int is mathematical integers, if you wish. Okay? Okay, great. So all the stuff that's purple is math, is logic. Okay, it's not Rust stuff. So that's why we index usize with an int and i32 with an int and so on and so forth. Okay, great. So now concrete things like 5 and bool true are all well and good. But of course you want to abstract over these concrete indices. So for example, I really want to write signatures that look like this. For any n, which is an index, if you give me an i32 that is indexed by n, that is an i32 equal to n, then I will return a boolean that returns true or false if that n is greater than 0. Right? Does that make sense? Imagine I wrote a function called isPos. I might give it a signature like this. Now, this is awful to write because, come on, who's going to write all these for alls? That's gross. But with a little bit of syntax, this becomes quite pleasant. Okay, so instead of this for all, we have this thing where you can write @n, where introduces a parameter name, except it's a refinement parameter. And then if you just kind of look, man, I wrote n colon i32. Can we just use the n for the then there you go. Okay, so now you can start writing signatures like so. A function that takes n, let's just go back and let's, for example, check this guy out. Okay, if I go back, I should have done this over here. I might write something like function isPos n i32. No, not that. If actually you just write n greater than 0, right? That would do the trick. And now maybe we would write something like, look at this AI. Okay, seriously, that's not what I wanted. I wanted n. I think it's gotten worse over time. Okay, so it should return a bool which is n greater than 0. Okay? What? Oh, right. Okay, fair enough. Okay, fantastic. So far so good? Back to the talk. Okay, jolly good. So, so I just showed you isPos. You can write other simple little functions like increment. It takes an n and returns an n plus 1. Here, let me show you two little examples. Okay, so there was, where is inker? I know I have an ink somewhere. No, not that one. I'll just go back to where I didn't want to show you all this. Here we go. Look at this guy. Okay, so for example, I take x, which is a u size, and I return x plus 1 because I'm doing x plus 1. Okay, so not super important. Here are some other little examples. Here I take a vector. I'm creating a vector with 5 elements, and so I can say that it's a vector of size 5. Okay. Here's a fun one. If I want to compute the length of a vector, if you think about it, that returns a u size, And I want to say that the u size is in fact the same as whatever the size of the vector was. If the vector was indexed by n, then I get back the number n. Everyone is following so far? Okay, great. Fantastic. So, for example, test length 0, this is super boring, but I might write something like assert that, I don't know, if I do, I don't know, let's make an empty vec, right? Let's just say v0 is equal to rvec dot new colon colon. Now we have to tell it what kind of vec, I think, because otherwise Rust is not happy about it. I32, and I want to assert that v0 dot len is equal to 0. Yes, yes. Autocomplete. Go, go. No, not like that. Not like that. Like that, yes. Okay? Okay. Great. So this is all well and good. Let's move on. This was indices. So now indices on their own are not terribly useful because it turns out that sometimes I don't know exactly what the index is. I don't know it's of length 5 or 10 or 22. Instead, I want to say it's a value b such that some condition about something is known about the index. Okay, so I'm going to introduce some syntax for that. B is a v such that p of v. So think of it as a set of b values indexed by v such that p of v holds. Okay, so there exists some v such that p of v holds for that particular value. So, for example, you might represent the set of non-negative I32 values as I32 v such that v greater than 0. Okay? Let's look at a quick example while we're at it. So here is, for example, scroll, scroll, scroll. Here we go. Suppose I delete this. Okay, so let's nuke some of these. So I might try, let's look at this guy first. So this is an absolute value function. It takes x and it always returns a value that's greater than or equal to 0. Why? I'm doing all this testing. If x is less than 0, return negative x, else return positive x. Pretty straightforward, right? Let's look at this one. This is, so imagine I want to write a floating point division function. I might write it takes x, which is an f32, and y is the u size, and I want to divide x by y. And so, for example, what I might do is I would put in, this is silly, you want to make sure that, for example, y is greater than 0. God help us. Sky is falling. No, just close it already. Okay, so assert y is greater than 0. And remember, I made assert take booleans that are only true. And of course, there's nothing here to tell me that y is greater than 0. Okay? So there's a couple of things I might do. I might make that a precondition. I would put that into the input of this particular function. So I might write something like this. Whoops, sorry. Flux sig, total noise. I won't do that. Instead, what I'm going to do is I'm going to define a type alias. Okay, so I'm going to say something like flux alias type pos is equal to u size v such that something like that. Okay, there we go. Yes, yes, yes. All of that. And now I can just change this u size to become pos. And Bob's your uncle. Okay, so that precondition is going to work out just fine. Okay. Okay, here's a more interesting thing. Remember to return to the subject of vectors and sort of memory safety. If I look at my little vector library, I can give the get function a type that looks like this. So this is using the primitives we've seen so far, except don't look at this and. For a moment, ignore it, just pretend you don't see that and. Okay? So it says get takes a vector, and a vector, remember, is at size n, meaning there's some n. I don't know what the n is, but n is the size of the input vector. And you give me an index, which must be a u size, because that's how it works, except that I must be less than n, which was the length of the vector. And in that case, whatever, it'll just call the actual get method, right? And the same thing for set. And so if you pop back over here, here is this little function that computes the Euclidean distance between 2 points. There's a little loop, newtres, and there's an index I, and yi is less than x dot len, di is x minus I, xi minus yi, and then it's like squaring it and adding it and incrementing the loop. Pretty standard, right? Can somebody tell me what the problem is? Why is it yelling? I mean, you could look at this if you like. Quick click for full compiler error. Okay, yes, let's click here. So it says precon that yi looks kind of questionable. In particular, it can't prove that it's within the bounds of the y. And why is that? What might we do to alleviate this particular problem?
Or set both of the vectors.
They have to have the same. they have to have the same dimensions, right? Exactly. So, oh Lord, fn. Oh my God. Okay. Sometimes it works. So here it says x is a blah 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 vec at n, and y is also, except the LLM is not that bright. You can only have an at one place because it's introducing a parameter, and now that goes away. Okay. So notice there is something happening under the covers here because there is a loop. So there's a bunch of things that are going on over here, which I have blindly skipped over. I was not supposed to get to this demo. Oh no, maybe it's fine. Yeah, there's loops and there's sort of array lookups and so on and so forth. Okay. So the thing that's interesting over here is that we've sort of moved beyond the abs, which was purely functional. Here there are updates, right? These little underlines. Notice I, which is being used as the array index, is getting bumped up. So there's some sort of analysis happening under the covers to make sure that that's okay. But let's get back and see what that is. Okay. So that brings us to the next bit, which is how do you handle updates? Well, there's the simplest situation is where in Rust what you have is what is called an owned location. So that the Rust compiler tells you, or the Rust type system tells you, that here I'm declaring a variable called x, and I'm declaring it as mutable, so you can change it. But x is the only thing that points to it. Okay, so x owns that location. X is, nobody else can muck around with it. And so what the type checker does, what the refinement type checker is going to do under the covers is it'll sort of let you update the type as you go along. So, for example, at the beginning, it's I32 at 0. But if I increment it by 10, it becomes I32 at 10. If I increment it again, it becomes I32 at whatever. Did I get this right? The math is right. Okay, you see what's going on? So it does quote-unquote strong updates because you have exclusive ownership. Okay, and this is what happened in that particular min index example that I just showed you, except that there was also a loop. Okay, so you have the same I, it is initialized at 0, it's getting bumped up inside the loop, but so the types are not quite the same, but it's okay because I is the only reference to that location, and we will actually assign it different types at different places. And I'll show you how that works under the covers later. Okay, so the more interesting things start to happen once you have pointers or what are called references. Okay, so when you sort of borrow, you create a location and then you create a borrow to it. And here there are sort of two things that we do. So the simplest thing that we do is this notion of when you have a pointer, if it points to a location, we're going to associate some invariant or some property or assertion, whatever it is, with that reference. And you have to preserve that. You have to simply preserve that invariant. Okay, so let's look at a concrete example. I might write a function called test, and let's look at what I'm saying in the precondition. So x is an I32. It's a reference to an I32, which is non-negative, right? Greater than or equal to 0. And so here, obviously, because I told you x is non-negative, if I take x and I dereference it, then the n I get is greater than 0, right? So there's nothing terribly surprising. But a brief bit of sort of rusties is, in this case, this is called a shared borrow, which means you can't mutate it. So if I just wrote and of I32, means I only have read-only access. I can't actually change it. Okay, so of course the invariant can be assumed and everything is great. The more interesting thing happens when you have an and mute. So and mute means it's a reference, and furthermore you can actually change what the reference points to. But what this particular type signature says is that if you give me whatever an x, which is supposed to be a non-negative, then by golly you must now make sure that that invariant holds. Okay, so if I have star x plus equals 1, fortunately in this case when the function finishes, that invariant is also being preserved. Okay, so there's sort of lots of work in the program analysis, program verification literature. Peter is sitting here, he's done much of that, which sort of has this idea where you have a reference and you have to sort of, you assume the invariant when you begin and then you must restore it at the end. And that's the semantics that we're going to associate with this and mute. Okay? So let's just go and do some demos. These slides are boring. Let's test update. Okay, we did all that. Min index, fantastic. So here we go. So now you might recall I have inc. So if I do inc x plus 1, very good, right? Look at this. So here what's happening is I have dec and I say and mute of pos and n is equal to star x, and I'm testing here, I'm checking if n is greater than 1, and then I'm decrementing. Can someone tell me what the problem here is? If you figure it out, we have something wrong in the condition. N is equal to star x.
1 plus 1.
What's that?
Plus 1 or equal.
Exactly. So this should not be a less than, it should be a less than or equals, right? And then it's fine. This is pesky little off by ones, right? By the way, this returning, this would be a good point, whose question about the U size, right? So suppose I change this pos to a U size, which is a more, U size is U size. And now suppose I did something like, actually, let me just replace this with true. I'm just trying to modify this as little as possible. Okay. So there you get this underflow check, right? That if you said it was a U size, you're decrementing it. That seems dodgy because it's clearly, it might actually, you might have a 0 and it goes below. And so here, for example, if I change this true to something like, what should I change it? If here it should be like if n is strictly greater than 0, right? This should be okay, I think. Then it's fine. Okay? Yeah.
So I could imagine, for example, you could do like a runtime check to make sure you're not going to overflow. And then you could have an else condition with mechanic. Does the refinement type checker also, because that could come from some, could you instead just use the assert macro, not the refinement assert? Could you do that and then if you like assert that if it's within the right range, it'll properly propagate?
Yeah. Yeah. Because, I think of this if as a runtime check. Kind of, right? But you could also use the assert macro to do the same thing. Yeah? Okay. Very good. Where were we? Here's another example where you have this. So it's a little strange. Why do we have this funny thing where you have mutation, but you insist that the invariance must be preserved? Well, here's an example. So here's a function called plus. It takes two vectors, and here what it's doing is it's sort of going pointwise and it's adding the ith element of the y vector, it's updating the ith element of the x vector with that, right? It's sort of absorbing these two vectors, if you wish. You'll see all these little fellows, they add up. They're not totally isolated examples. Okay? And so now again you get this refinement type error for the same reason. So let's see if we can belch out a spec for this. Flux, sig, fn, what should it be? Come on. Apparently it is not obliging. I don't want to type all that. So I'm just going to copy this. And then I shall flux sig, fn, blah, 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 new call that. Close. Okay, now over here what I want to say is at n, and over here I want another at n. What? Oh yes. Go away. There we go. Okay, so now it's the same deal. They just have to have the same dimensions. And now notice that we're not changing the dimensions of the vector. Okay, so the vector size remains the same. And in fact, that's what the set specification also says. Okay, so if you look at the spec for set, it says, you give me a vec, you will mutate it, that's great, but you don't actually change the dimensions because set does not change the dimensions. Okay, very good. Now this is all well and good, but it's a little bit tedious because of course sometimes you have a reference, and I said we're going to do imperative programming, you need to actually change what the reference is changing, is pointing at, right? So if I wrote something like this, if I wrote this inker, the same inker that I had before, and then I tried to test it out like this, if I said let mu z is equal to 1, inker and mu z, okay, so this creates a reference, this creates a pointer to it, a reference to it, a mutable reference to it. I would expect to see that over here z is in fact equal to 2. But this sort of summary or this specification that we have for inker is far too strong, it's far too weak. It says it's non-negative, that's all I can tell you. Okay, and so over here this assertion would simply fail. So let's, if I tried it out, you would sort of see this. Let's pop back over here. Where did my inker go? This cheats. Okay. Where did the old inker go? Oh, here's the old inker. Okay, so here's pos, right? And so if I had something like this, if I had function test pos, and what does it do? It says let mute x, okay, fine, is equal to 10, good enough. And now I call inc of and mute x, okay? And now I want to assert that by golly, x should be equal to 11, yes. Thank you. It's like, sorry, I can't prove it. Okay, at best I can prove to you that x is greater than 0. Right? That's pretty much the only thing that I can prove to you because that's all we know from pos. You pass in a pos, it stays pos, etc., etc. So this is kind of annoying. And so instead, what we have is another thing called a strong reference. And the surprising thing about strong references is how sparingly you need to use them, but sometimes you need to use them. Okay, so what I'm going to do is, I'll just do it sort of in place, right? So here what I'm going to say is, the signature looks something like this. No, not kind of. It takes a strong reference to a pos, And it ensures, okay, so ensures tells you what is the state of the reference when the function finishes, and it's also going to be a type, is going to be, what lord, let me not use pos here, I'll just use usize or whatever, I32, let's just stick with I32, I've forgotten what we were doing. Strong reference, la la la, ensures that when I'm done, X is going to be an I32 such that what? So you have to somehow know what is the value afterwards, and so I'm going to say the value is equal to n plus 1, where, what the hell was n? N is what the value was upon entry. Okay? And so now you can sort of recover this fact with any luck, that X is equal to 11. Okay? So let's pop back to the slides. So this is what it looks like. Okay, so I can write something like this. Incr takes a strong reference to an n, and it ensures that whatever, when you're done, it's n plus 1. Okay, so this is again not, it's, nobody cares about increment, but maybe you do care about things like this. Let's look at the push. Let's look at the push method again. For the vector API, it says I take as input a strong reference to an n, and I ensure that when you're done, there's one more element in it. Okay, so there's some other stuff in the signature that it's polymorphic on T's, and we'll get to that in due course. 2 questions. There was one over there, and yes.
Maybe you're about to get into this, but what about mutable references? Like, why do you need a new type of reference? Like, why couldn't we do a mutable reference and then also the ensures one?
It's a funny thing. My student Nico gave a talk at that workshop in Paris, and we've been doing this for 2 years. It never occurred to us that we could do that. And Nico Matsakis is like, why don't you just use and mute and then have the ensures to say that it's a strong reference? And we were like, oh. But you're right, you totally could. So it's just a totally syntactic thing. The and mute has this. There's a difference in semantics. And mute says thou shalt preserve this invariant. The and strong says you don't have to preserve the invariant, but you can actually change it. And like I may have alluded, we found you rarely need this. You need this far more rarely than you think. And the and mute is actually quite convenient because for the most part, you have a reference, you're mutating it, but you sort of, you quite nicely, firewall or what's the word I want? Sandbox the changes. And you just sort of break the invariant locally, do some stuff, reestablish it, and you're done. And so it sort of makes the specs quite simple. Did you have a question? The same question, right. So it's quite convenient to have both of these, okay? Because often you don't really want strong updates. So one gives you what in the program analysis literature is called sort of weak updates, and one gives you strong updates. Yes, Peter.
So is the observation you just made, is that because your specifications are super interesting but still relatively weak, right? Because if I take a mute, I declare the mute because I want to change it. You're saying, but usually I don't care about the change in the spec, it's an invariant and there it's preserved.
Exactly.
So if you make your specs stronger, then you also need more of these strong.
Then you would need, correct. That's a good way to put it. So if your specs are sort of weak and very broad, then you tend to preserve them more often, I think is what you're saying. You change them less frequently, right? Okay, where were we? Right, okay, push. Oh, range, I wanted to show you range. Range is a fun one. Range, here's range. Okay, so here's range. Oh no, precondition does not hold, what a shame. Well, here's range, and it takes a low and a high, and here what it's doing is it's sort of spinning around in a loop, and it's sort of taking these numbers from low to high, and it's pushing them into res. Right? So res is this vector you're building, and you return the vec. And what I would like to show is that if you give me a low and a high, then I get as output, and now there's quite a bit that's happening in this signature. Let's stare at it for a little bit, okay? It says that I am an RVec, okay, and every element inside me is a U size, but furthermore, it's a U size that is between low and high, okay, because that's, hence the name range. And furthermore, the size of this vec is high minus low. Okay, because you use like range 5 to 10, whatever, there should be 5 elements. Modulo some off by 1. Now it's entirely plausible that I have an off by 1 here, but in fact, the error here is far more innocent. It is simply that we need a precondition on this function that low is less than, exactly. Low is less than or whatever equal to, I don't know, let's just try this. Since you said less than, okay, fine, it's happy. Who am I to complain? Okay? And again, you can imagine there's a bunch of analysis going on under the covers here because there's I, there's changing, and so on and so forth. Okay, and in fact, there's okay, never mind that. We'll get to that guy later. Okay. Okay, fantastic. How am I doing on time, by the way?
You still have 5 minutes.
5 minutes, great.
It's a question from remote people.
Okay. Okay, good. Okay, so there's a longer. Maybe we just skip the analysis part, and I'll show you how these pieces all add up. And there's this much larger example that sort of uses many of these pieces that I might as well. I'll show it to you very briefly because it's quite cute. So what I did is I took all of these things like range. It takes these vectors and these this add and distance and so on, and then you can write, for example. Here's a small little MapReduce library. I'm putting it in quotes because obviously there's no, the implementation here is fake, but the only thing that the analysis cares about is the types. Okay, so for example, here's a map function on vectors. It says if you have a vector of t's and a function that takes t's to use, then you get as output a vector of use. That's what it says. And furthermore, I guess in this case, the length of the output vector is the same as the length of the input vector. That's what this guy is saying. Here's a group function, so it also uses hash tables. Okay, so here what this does is, if you have a vector of keys and values, and you have whatever this, you can k is comparable and so on, you get back as output a hash map where these keys are all going to be grouped by k, and each key gets mapped to its vector of values with that same key. Okay, there's some like stuff underneath, and finally there's a reduce, which is like a fold, and again they're all they're imperative and so on, but there's nothing fancy. These are literally just the Rust types, right? And if I have a hash map of keys and this this vector of things that each k was associated with, then I will take this vector and squish it down into a single v by applying this f function that combines v's and crunches them together. Okay, so this is a pretty standard kind of MapReduce deal. And what you can do is you can then sort of write this little k-means clustering algorithm, which is doing all this stuff, right? So it takes as input n, which is whatever, I don't know what n is. Oh, n is the dimensionality, there you go. It takes some number of starting centers, which is going to be a vector of points of size k. Okay, so I keep k of these points, but k should be non-negative because it should be strictly positive. And it takes a collection of points. It's a vector of points, each of which is of dimension n, so we want to make sure they all have the same dimension. And here it does all these shenanigans, right? It's doing this, it calls some function, it's mapping each of the points to its nearest point. There's a whole bunch of this array bounds checking. And there's this reduce function, there's a higher order function. And in all of this, remember I promised I would use this fdiv. At the end, you sort of collect these clusters, and then if you know how MapReduce works, you build these. You start with some clustering, then you build a new clustering, and then you sort of normalize the points by the size of that cluster, which is where this fdiv operation came in. And so we were actually doing a division there, and this requires you to track the fact that that each of these clusters is non-empty, and it all works out very nicely, just sort of plumbing through the types, right? So in my 5 minutes, maybe I will try to explain a little bit as to how this particular analysis works. Okay, I'll just give you I'll be very fast, okay? So it turns out that this business where we sort of take these little logical predicates, assertions, and stick them in the types is not only cute, it's not only kind of easy to write specs, it makes the program analysis a lot simpler, okay? And it's specifically what I had 2 examples, I'll post the PDF or whatnot, which talk about how it works for collections and updates, and then how it works for closures and higher order functions. So let's just do the first one, which is collections and updates, okay? And the key trick is this. The job of the program analysis, you should think of it as, when I wrote those little logical predicates in purple, the job of the program analysis is to synthesize those. Like, I don't want to have to write them down everywhere. I want the analysis to figure those out. And what I'm going to do is, when I don't know what the predicates should be, I'm going to introduce these little templates, and I'm going to generate constraints to solve for them. So I'm going to start with my code, and I have this type checking procedure that's going to generate horn constraints. And then once I have the horn constraints, I'm going to use an SMT solver with a little fixed point loop around it to solve those horn constraints and say either yes or no. So I'll go through one example really, really fast. Okay, so here's that range function that we saw. Low, high, low is less than high. I have to produce a vector of this size. Now here, of course, I wrote the spec, but what is it that the analysis has to analyze? Well, so first of all, there's There's a collection there, there's an update there. But here's what the analysis has to figure out. What types shall I give to I and res? Because these are things that are getting mutated, and what do we know about this, right? I didn't have to write anything down. So here's the plan. The plain Rust type looks like this, right? I take a U size and I take a res, which is a rvec of U size. And so what I want to synthesize, what the analysis must figure out is I is a U size such that what? And res is a vector such that what? Okay, so notice this, if you write it as the synthesis people have taught us with question marks, you might imagine it like this, right? U size with a question mark, U size with a question mark, and then there's an extra question mark for the size of the vector as well, right? And so now the key idea is, as my mother taught me when she taught me how to do algebra in whenever it was, 6th grade, is that when you have an unknown, you introduce a variable for it, okay? So wherever you have this question mark, I'm going to introduce, these are called horn variables. Okay, so I'm going to introduce, there's some ki, which represents the unknown invariant for I. There's some k val, which represents the invariant for the val component of the vector, the value component. And there's another k len, which represents the unknown for the size of the vector. And now once you do that, the type checking, you just pretend you knew those types. And the type checking sort of generates a thing like that, which looks scary, but let me try and walk you through it really, really fast, okay? So here's the precondition, and it says low and high were U sizes where low is less than high, so the constraint says for any low, for any high, if low is less than high, this implies is like an if, right? It implies that, now keep going. What do we know? I equals low, it's an assignment, right? And remember I said that ki was the invariant for I, and so ki must hold for the value low. That's what this constraint says. This is like an impressionist view of what the constraints are supposed to look like, okay? I don't expect you to really fully sort of get all of it, and oh god, these colors look awful. But res rvec nu, remember the length of the vector at this point, so k len of 0 must be true, because at this point I'm taking an empty vector and sticking inside res, and I have no elements inside it, and so false implies it's a kind of degenerate constraint. We can skip it. Oh, it's a lovely pink on my screen. Okay, while I is less than high, now again this was the loop invariant, and remember we've assumed that k len holds for n and ki holds for I, and so we're going to say for any n and for any I, because now we're sort of checking the loop body, right? So we don't know which iteration we're in, so we're going to say for any n and for any I in some arbitrary loop iteration, as long as those two properties are true. And now you have two conditions. One, inside the body, I is less than high, because that's coming from the branch condition, I is less than I. Where is this rest dot push coming from? Well, first of all, remember we took this I and we stuck it inside the vector, and so k val of I must be true, because I'm literally taking I and sticking it inside the vector. And this sort of falls out of the way we have this polymorphic type signature for vec. I equals to I plus 1, well then k of I, whatever that invariant was, must also be true for I plus 1. And finally, k of len of n plus 1 must also be true, because this push increments the length of n, right? Finally, in the else branch, what do I have? I'm returning res. And so what do I know? Well, if I is not equal to high, because that's how you break out of the loop, n is equal to high minus low, where did we get that? Oh, I have to prove that, right? If in the else branch, I must prove this post condition, that the size of the vector, the number n, that same n, must be equal to high minus low. And furthermore, each of the values, if they satisfy k val, they must be between low and high. So essentially you get this just giant horn constraint, and there's various sort of pretty standard fixed point algorithms that will solve them out and give you a solution that looks like so. Sorry, we're way over time? Oh Lord. Well, that's a signal perhaps for me to end. Let me do the old thing. Why does it stop working, I wonder? Come on. Oh, we're back. I shouldn't have messed with. Wow, that's funny. It doesn't show half my screen though. Okay, let's skip all of this in the interests of lunch, and let's let me just make some concluding remarks. So, I mean, a lot of this looks very much like Floyd-Hoare logic. And so the closest comparable tools are all based on Floyd-Hoare logic, like Peter's group has been building Prousty that we compared against, but there are several others now. But what we wanted to show is that when you have these relatively simple specifications of, like this overflow or arithmetic overflow, underflow, array bounds checking, that sort of thing, the kinds of invariants that you get from free from program analysis are really quite a nice win. So when we started this work, Prousty was pretty much the only game in town, but now there's several others like Crusoe and Verus. And I should point out that these are significantly more expressive. They let you say far more sophisticated sort of full functional correctness properties. So we're looking at something much simpler. But with that in mind, so we took a bunch of benchmarks and sort of wrote them in both of these tools. So Prousty is the sort of program logic style, and Flux is with a bunch of this kind of program analysis under the covers. And I guess the high level bit is that you get a bunch of really nice invariants just for free from the type. So in Prousty, you have to write down various loop invariants. I'll show you some examples in a minute, which you simply don't have to because we've sort of simplified the specs in a way that they can be automatically synthesized by this fixed point loop. And furthermore, I guess partly, we conjecture. We have not done a full profiling, but the types sort of make the SMT queries much simpler. So Prousty also uses an SMT solver, but they use what are they called? Quantified assertions, universally quantified assertions, which are sort of more work for the SMT solver. And Prousty does a little more work to do the memory sort of consistency checking, if you wish, all of which get eliminated by the types, and so the check becomes somewhat faster. So what are the kinds of invariants that you might get? So here is, the fonts are a little small here, but here's the same range function in, this one is Flux, I guess, and that one is Prousty, I think. But here, for example, you notice there's all these invariants that you have to write down about I being between low and high, which will automatically synthesize. But perhaps the more interesting one is this one, where notice that in the Flux world, we just said it's a vector of things where each thing is between low and high, right? And so the rvec was essentially saying for all my elements. While in Prousty, you have to, because it's all in logic, you have to sort of spell that out explicitly with a for all, and which ends up with, sort of shows up in the spec, but also in these loop invariants. That's why the screen broke. No, that just happened this time. I guess I should not move so much. But I'm almost done here, so let me just cut to the chase. Results very good. And so, let me just sum up. This is what no, don't finish already. What is it doing? Here we are. This is my last slide. So, I hope I have persuaded you. Oh, God. Here, I'll just do it this way. Let's do it the old-fashioned way. Espada will be very sad. I hope I have persuaded you that to not think of things as just program analysis, but as the programmer's analysis. So now get the programmer in the loop. And I hope I also persuaded you that refinements are one way to do this. And we kind of skip the abstract interpretation bit, but such is life. And if you like, you should go check out the tool. It's on GitHub. It's pretty fun to play with, if I say so myself. Thank you.
This is really cool. It's especially nice how fast the checks are. So how do the Rust people react to that? Are they open at all to extending the language to something like that?
Give me 1 second. I don't, that's a good question. We have not, we've had some chats with Nico, Matsakis and so on. I was literally, until yesterday, I was very excited by something called proc macros, because we were like, oh, we can use proc macros, and you don't have to write these pesky specs in this bound style. But it turns out you can't. And Nico, my students, like, no, Renji, that I just realized proc macros, it has to be well-formed Rust. So this does not fly. So I don't know. That's a good question. I hope so, but I think you have to it probably takes some more persuasion. You have to show them enough of a value, right, of this kind of thing before making such a large change. That's why I said yes. Sorry. Max. Let me see if I can fix this. Next speaker.
Yeah, thanks for the talk. I noticed for the base types, the type that you were using to refine was sort of like, isomorphic-ish to the base type. Like you were using bools to refine bools and ints to refine like U-sizes and stuff. But for the vec, you chose a different type. And so is that somewhat of an art? It seems like you're sort of limiting what you can say about the vec. Like you can't really do theory of arrays sort of stuff, like saying, when I store something there, it's actually there. If you choose length as the refinement. So how did you choose that? Like, what does that look like when doing more bigger code?
Excellent question. So the short answer to that is that for the base types, I think there's only one sensible thing to do, right? Whatnot. For VEC and other things, you can imagine lists and trees and whatnot. If you're familiar with Liquid Haskell, as I know you are, a little bit at least, you should think of the index as a way of encoding the measures. So basically, whatever measure you like, you can make an index out of that. And really, as I've learned from Neil Krishnaswamy recently, that's really what's also happening in Liquid Haskell. Is under the covers, you should really sort of, from the meta theory point of view, think of it as a measures getting. So when I picked, so the one unpleasant thing here is that you have to kind of bake the index in, and that's bad. But I think that's just a syntactic restriction right now. Really what we want to say is that you define a VEC in one place, and then here are n other things, and then they all get compiled down into, so what I didn't show in any of these examples, you can have multiple indices for any type, right? So for all the ones we saw, there's only one sensible one. But if I dig up, for example, one of the big case studies we did was this wave, which is my colleague Dejan Stefan built this verified WebAssembly sandbox. So then you have this giant sort of virtual machine context thing with like, I don't know, 10 fields. And so that has like, 7 different indices.
So like, why not index all types based on like all of their contents? Like, you could go all the way down and index everything by everything. I assume there's some sort of performance cost or something at this point.
Well, remember the indices, the main constraint is the index has to be something the assembly solver understands. So that's the one thing you have to kind of, it's all pure. In index line, everything is pure. So often when you do have structs, you end up essentially creating multiple indices for each field or things like that.
So we have one more question. Perfect. Thanks for the talk. So at the start of the talk, you mentioned that prior work had looked at sort of refinement types for sort of functional languages, and kind of motivation was that a lot of code was written, or like people wanted imperative languages. So my question is kind of, so besides that motivation, over the course of like actually implementing the tool and verifying things in it, have you found things that were actually easier to verify in this particular domain as compared to sort of something like Liquid Haskell? And sort of a related notion is Liquid Haskell sort of after development has been used to verify kind of a range of things beyond just sort of programs. Sort of it's used to verify distributed systems and sort of differential privacy, etc., by embedding these different domains into that. And sort of a question in that line is, do you think something similar will happen with Flux? And are there particular areas you might think are more amenable to integration with Flux as compared to something like Liquid Haskell? Thanks.
The first one was, what was the first one in a nutshell? Is there something that's easier to do?
Yes, easier.
So certainly the thing that's much easier to do in this style is verify imperative code. Second is with Liquid Haskell, because I mean, one has this, really gets in the way. So that becomes much easier.
But for example, like k-means, right? I mean, k-means has been verified in Liquid Haskell as well.
Right, but you have to write that in a very functionally style.
Right.
In order to be able to use. So I think the way I put it is, if you're writing in an imperative style, this is much easier to work this way. The second question was, you could do n other things with LH, and I mean, I think the real answer to that question is it depends really on how long it keeps working on it, because I think that those n things happen over a span of like a decade or something, right? But I think what the sort of the skeleton that I showed you for Flux shows you how you can start with something that's very imperative, but reason about it in a very pure fashion. And the reason it works is, that as Simon Peyton Jones said, when somebody says something is free, it means you've already paid for it. As with lunch today. So in a sense with Flux, all of this reasoning comes for free because you pay for it by getting all your code to pass through the borrow check. Right? And so really, if there's one high level observation here, is that the borrow check has sort of made you sort of force you to write the code. It looks imperative, but if you squint at it, it's actually super functional, right? And we tried to do this several times in the past, and it never felt right. And now it feels like kind of like it.
Okay. Any other questions? Okay, one more.
I think there was at least one slide where you talked a bit about how, like the performance of the tool itself. But I'm just wondering in general, like, have you tried running this on like a very long function, like let's say more than 100 lines? Because to me at least, I'm not sure how, I mean, when I think about using like an SMT solver and like some form of type checking, the hair on the back of my neck starts to stand up a little bit because I think about, Rust already has kind of long compilation times. I'm not sure if those want to get much longer. Yeah, I don't know if you have any thoughts on that.
More than 100 lines, I'm trying to think. I think, that's a kind of factor. I don't think that, to be quite honest. I mean, we thrown it at large chunks of code, but have I thrown it at a function that's more than 100 lines? I don't think so, right?
I did that just as an example.
But it is, I mean, yeah, I can't pull up the slide because it's really hard and I don't think it at this point I was that range. It would affect, but I mean, I will say one thing, which is that the way we've set up the type checker, the SMT queries are very, very cheap. As SMT queries go, of course. I mean, it's all NP complete, right? So, modulo of that, there are no quantifiers in particular, right? So, because there's no quantifiers, the queries themselves are quite straightforward. So, they're not quite so bad. So, it does, with some amount of caching and so on, that's why it feels so fast. It does kind of, and with a lot of the code, it's also the way I see it. For example, if you're editing this 100-line function, you will only be checking that and that. The reason it's fast is because every time I hit save, it was only checking that one function, or the bits that one function depends on. So my hunch is it's not so bad, but I think ultimately only time is done.
Okay, we are 15 minutes over time, so let's grab Ranjit over lunch, but let's thank the speaker again.